Okay, so hi everyone, this is Sean Mullery from Electronic Engineering at IT Sligo, and what I'm going to be doing in tonight's lecture is projective geometry. So this is the first of two parts on this sort of material, where we're going to be looking at projective geometry first of all, and then next week we're going to look at the actual modeling of the camera and how we would actually discuss, you know, how the camera would do a projective transform on the 3D world, but that'll be for next week. For this week we need to discuss the whole idea of projective geometry first of all. So we need to start with firstly maybe talking about what is geometry. So geometry deals with properties of figures, in other words drawings or diagrams in the plane or in a space. Okay, so in the plane would mean on a sheet of paper, you can think of it as that, or in a space, in a three-dimensional space when we talk about it. But of course, it could be in a larger space than that as well. It's just that the ones that we're used to seeing are the ones on a plane or in a 3D space, but it could be in a 4-dimensional, 5-dimensional, 6-dimensional, and so on space. So there are lots of classification methods to break geometry down into different parts for deciding which part of geometry that you're working in. But one useful distinction that I found quite useful when I was trying to come up with something for these lectures was the idea of synthetic geometry and analytic geometry, and I'm going to go through an explanation of what those are so that you kind of get a sense of where we are. So synthetic geometry first is what most of us think of as geometry. So it's this idea where, you know, we draw lines and circles and triangles, and we have angles and so on, and we try to, from that, build up theorems and try and build up information about things. So, you know, one example is Euclid's Elements, which I'm sure you covered many of these back when you did Leaving Cert or equivalent. You would have looked at many of these theorems, and this is just one example of one of the theorems from Euclid. And you can actually get Euclid's Elements as a book on Amazon or anywhere, and it goes through all of these different theorems if you ever want to have a look at them. But the thing is that all of the proofs are carried out using just straight lines and circles and so on, where we don't know the specific length of the line, or we don't know the specific radius of the circle, but nonetheless every figure can be built from the picture alone. And so what Euclid does is he starts with a fairly simple line, and then he draws a circle related to that line, and then he builds up from there all of his different theorems. Then he proves, well, if this is the case, the next thing must be the case, and the next thing must be the case, and so on. So you'll see that while the lines are represented by letters there of particular, given a particular letter, and that suggests the name of it. What we don't have is we don't actually have specific numbers related to any of the lines in order to prove any of these things. We can just work from the detail that we have there and build it up. So that's the idea of synthetic geometry. So this idea of building up from simple parts using logic and reasoning is what is meant by synthesis. So hence synthetic geometry. So that word synthesis, or when you talk about something being synthetic, what that basically means, we often think of something being synthetic as maybe something being man-made or being fake, but all it means is that we can build things up from small constituent parts up into a more useful whole. Okay. So, for example, when they find something in nature that's useful as a drug, they break it down, find out what are the constituent parts, what are the parts that are useful in terms of treating some health problem, and then what they can do is try and synthesize that in much larger amounts from those simple constituent parts. So that's what we mean by synthesis or synthetic geometry. Now, analytical geometry, on the other hand, is based on the introduction of numerical coordinates and uses the techniques of algebra. So once you start putting numbers to any of these points or these lines, you're now into the idea of analytical geometry, and it means that you can now use all the techniques of algebra in order to help you solve the different problems that you're trying to do. So in other words, if you're trying to prove some theorem or otherwise that something must be the case, you can actually now use all the techniques of algebra. Okay. So for a long time, those were completely separate, the idea of algebra and the idea of geometry, but then they were brought together in this way. So by doing this, geometry, analysis and algebra were all brought together into one system. So to begin with, we normally always refer the algebra back to some picture or figure as if to prove that it is not just some sort of mathematical magic. So you find that we tend to do that. The algebra is fine, but it's so abstract for us that we tend to find it a little bit difficult. While we can follow all the rules and follow all the manipulations that we're supposed to do, we often find it difficult to get a sense of what's going on. And so what we have a tendency to do is always try and say, well, okay, this move that we've made here, that's equivalent to that line going over in this angle, or that's equivalent to those two lines crossing each other and meeting at a point, or whatever the different things might be. But by using algebra, we can actually free ourselves of the drawings entirely. And you know, when you consider drawings, try as you might, they'll never really be exact. And you'll see some of the drawings that I've made, they're far from exact. They tend to be pretty poor. But even aside from that, when I'm trying to draw 2 or 3 lines meeting at a point, I find it very difficult to get those lines to meet specifically at a point. What normally happens is they cross over and there's maybe a little triangle in between them. Or if you zoom in on it, you can see that the thicknesses of the lines, they kind of overlap, but they don't necessarily all meet exactly in the point because they overlap at different places, and in certain places they don't. And that's part of the problem with the analytical geometry idea, is that we can never really be perfectly exact because our lines can't be zero thickness. And we can never exactly land perfectly to a point. So if we want a line to end perfectly at a particular point, that's very difficult to do. Whereas once we get into analytical geometry, that's all taken care of by the maths, and we can be perfect. Now, I did say to you in the very first lecture that you need to be wary of that idea that while maths is perfect, our real world can't be. But it does mean that we can do an awful lot of work in this analytical geometry zone in order to then figure out something else that's going on. So in much the same way that imaginary numbers allowed us to find solutions to problems that couldn't appear on the graph. Now, I do know you can graph imaginary numbers on a Cartesian plane and so on, but I'm referring to, you know, when you used to solve those quadratic equations and you'd be looking for the roots of the equation, and which were the points where it would cross the zero or cross the x-axis. And you then had one of these quadratic equations that didn't cross the x-axis, and therefore you had imaginary numbers as a result of that. They didn't appear on the graph, but nonetheless they were useful in mathematics in order to solve something. So it's very much the same here. Analytical geometry allows us to use all the systems of algebra to produce a final result that, should we need to, we can usually show pictorially. Okay, I say we can always show pictorially, but actually, if we're up in higher dimensions, that's not always the case. But it does mean that we can often go through many different transformations, all of which we don't have to be able to visualize exactly what's going on, and then we can come to a final result. And if we want, we can try and bring that back to some pictorial view, so we can say, now look, here's where we are now. The trouble for any student, and I include myself in this as an ongoing student of any of this stuff, right? So the trouble for a student is that you can see synthetic geometry. You can see the lines, you can see the circles, and diagrams work really well. And of course, that's because humans evolved to such an extent that their eyes were the primary source of information that they get. So it makes sense that when we see something pictorially, that works really well for us. Okay, but we can't see or interpret each of the steps in algebra, and therefore it's a matter of knowing the rules that are involved in it and making sure that we keep to those rules. If we have kept to those rules, we can be sure that what we're getting is correct and that the manipulations we're making are correct. Now, if you can come to accept this and get a little bit beyond the idea that you have to be able to visualize everything pictorially, that will really pay you dividends. So if you learn that the set of rules, that maths is all really about just a set of rules, and if we stick to those set of rules, we'll be okay. So if you can do that, it means that you can make much faster advances in what you're doing, where you don't have to every time see that lines are crossing, or that, you know, a circle is a certain shape or whatever it might be, or an ellipse is hitting 5 different points, or, you know, all these different things that once we've seen them once, we should be able to say, well, okay, now that I know that we can just explain this as algebra, we should be then able to just move on from it. So theorems of elementary geometry are based on lengths, which are generally magnitudes, are measures of angles, or areas and volumes. As we said in earlier lectures, there are geometrical transformations that can take place on figures that, while changing the figure, will retain some properties that are common to both the original and the transformed figure. So if you remember, we looked at basic translation, and then we looked at the rigid body movements, and we talked about what properties of the figure that they preserved. Okay, so this is the idea when we talk about geometry. We need to think about these things, about what's preserved, and about what in the algebra we would have to know. What we would have to know in the algebra in order to know that these things were maintained. So, for example, last week we went through some of the mathematical kind of scaffolding for the different ideas, like if we were going to have a rigid body motion, that we would have to preserve angles, and therefore we would have to preserve cross products and so on. Okay, so we had a lot of that information, and as long as we know that then we're obeying those rules, or we can test that with the algebra, it means that we don't have to necessarily see that the figure has retained these things. So describing the properties that are retained in an algebraic fashion as opposed to just in a diagrammatic fashion becomes useful for determining how a figure will change due to a transformation. Okay, so this is where we're trying to go with this. So congruence is the algebraic or mathematical term for the rigid body motion that we mentioned previously, and we can, of course, the rigid body motion makes a lot of sense to us intuitively, whereas congruence is very much just a mathematical term. So if two figures are congruent, then they contain the same magnitudes and angles, but not position. In other words, it's moved to another position, and that means that it could have rotated and it could have translated. Okay, so rotation and translation, or the rigid body motions, are covered by this. So previously we came up with algebraic formulations for these rigid body motions, such as translation and rotation, and we showed that they retained the magnitudes, such as the scalar product, and the angles via the cross product. And of course we also showed that via the triple product that came after it, that we retained the volumes in 3D objects. Okay, so if something is congruent, that's just a mathematical term for the rigid body motions that we have. Now, when we went through all of those, we saw that if it was just translation, that preserved an awful lot of things. Okay, so it even preserved its orientation. And then when we went to the rigid body motions, we saw that it preserved straight lines, and it preserved parallelism, and it preserved lengths and angles. And then when we went down further to the affine ones, we found that it preserved certain things but not others, right? And each one we went down, we lost something in what got preserved. And when we got to the bottom of that pile was the projective transform, which in our list of geometrical transformations, this was the one that preserved the least, the idea of the projective transform. So all it preserved was straight lines. It didn't preserve angles, it didn't preserve orientation, it didn't preserve position or any of that sort of thing, and it didn't preserve parallelism either. Okay, so it sounds very limiting, but actually ensuring that the straight lines in a figure are preserved under a transformation allows an enormous amount to be determined. And this is very important in computer vision because figures in the real world undergo a projective transform when being captured by a camera. So therefore, if the projective transform was not of much use, we would find that actually taking images of things was not particularly useful when it came to trying to reconstruct the world or otherwise. So this class of transforms and the preservation of straight lines becomes our primary focus then, even though it seems the most limiting of them. So the study of projective geometry was considered long before the introduction of the camera. You had artists such as Da Vinci who took it into account in order to draw realistic images. So before that, you saw a lot of the images in art were very flat. They had no three-dimensional element to them. Whereas if you look at something like the Mona Lisa, you will see that there's things off in the background and they get smaller and smaller as they go. And that's in some way looking at projective geometry. So the real world is projected onto the canvas by the artist, and the eye of the artist or the painter is the center of the projection. So it's drawn from the perspective of the painter. Therefore, the resulting image can be considered a perspective. Okay, so these are the kind of terms: the perspective and the projection. They're both related. Lengths and angles are all distorted, but in a way that is dependent on their relative position. So it's not like they're just distorted in some sort of arbitrary or random sort of way. They're very much distorted, related to where they are in the image and how far they are distant. So as the human eye is used to seeing the world from a perspective view, admittedly with two eyes, and therefore we have some idea of depth there, but we're used to seeing a perspective view, so then the geometrical structure in an image can usually be recognized as well. So when we look at an image, we normally have a good idea of what's far away. Now I'm sure many of you have seen lots of examples where you can be fooled into thinking that it's something else. Where you have a chair off in the background, but it's actually a small little chair or something like that. And from one particular perspective of the camera, it looks a certain way. But as soon as you move the camera, it then looks differently, and the human visual system immediately recognizes that it wasn't quite what it appeared to be. Okay, so I think I'll just I'll assume that that previous slide has been covered, and we'll go to the central projection here. So. As I was mentioning there earlier, we have a tendency to use the word pi, or the letter pi, in order to denote planes. So it's something to get used to, because oftentimes when you see pi, you automatically assume that it's that universal, that constant that we use in order to relate the radius of a circle to the circumference. But actually, we have a tendency to use it to describe planes. So we've got two planes here. One is called pi, and the other is called pi prime. So try and get used to this mathematical notation. By the way, when you see that little tick mark up on the side, that's known as pi prime. So if you see that little tick mark beside anything else, if it's beside an x or it's beside a p down here lower, we would call that p prime. Okay, so. We have two planes, pi and pi prime, in a space, and these planes do not have to be parallel to each other. So when I say they don't have to be parallel to each other, I'll just grab I tried to grab two sheets of paper there, and it managed to rip on me. Come out. Okay, so if we take two planes here, we could have them, just maybe. Okay. So we could have them like that. Okay, so we've one straight along here. Okay, and the other one up like that. So it's not that they don't just have to be parallel along their lines here, like I've shown them at a kind of a different angle. They don't even need to be parallel to each other along any axis. Okay, so we can perform a central projection on pi of pi onto pi prime. Okay, so off the kind of purple one here, or the pinkish one, onto the orange one here. Okay. So Niall is asking a question here. I'll just hang on to just see if. Nope, gone. Okay, that's no problem. Okay, so we can perform a central projection from pi onto pi prime from a given center, which we'll call O. And that center, it's important, can't be lying on one of the planes. So it has to be somewhere off the plane in some direction. Okay, so. So it can't be either on pi or on pi prime, but by defining the image of each point P. Okay, now I've only shown one of the points as being called P, but if you look there, I have drawn 4 points. Okay, well, I've only called one of them P, but you could call them P1, P2, P3, and P4 if you wished, in order to say where they went. Now, what you'll notice here is that 3 of the points all lie on a line. And what we're trying to show here with this is that if the points lie on a line on one plane, then they will lie on a line on the other plane as well, when we project through from a central point. Okay. And the important thing then is such that P and P prime lie on the same straight line through O. Yeah, absolutely. It certainly would be. So if Niall is saying there, if anybody did did technical drawing for the Leaving Cert, this sort of thing would be on it, absolutely, yeah. And you may have come across it in maths as well, okay? And we're going to show you another one as well now in a minute, which is probably, I actually only did technical drawing up to Junior Cert, so I didn't do it for the Leaving Cert, but I've come across a lot of this in the past as well, okay? So yeah, there is a gap between the planes, Vince, absolutely, or this wouldn't work. It's just that it's very difficult for me to draw it, okay? So absolutely. So what I'm talking about here is that I'll just maybe just put that there. So I'm talking about one plane here, and the other plane is somewhere above it like that, but it doesn't have to be parallel with it. Okay, and that's the point that we're trying to make there. But it's very difficult. I've never been great at drawing these things. I tried to copy this figure from a book. Their one was slightly better than mine, I have to be honest, but I did my best with it. But anyway, that's the idea there. So we also have this idea of a parallel projection, and this one is probably even more memorable from technical drawing, because what you used to do is you used to do these projections off to you'd have a plan elevation and an end elevation and so on. I'm going a long way back in my history to try and remember these, or the different views of it. But the parallel projection doesn't have a central point, okay? So these lines all just go off in any direction, okay? So at the start, what we always do is we always talk about the one with the central projection, and then we say, oh, by the way, there's also this parallel projection as well, just to mention it, okay? And you can get the impression straight away that we're not as concerned about this parallel projection. Now, one of the reasons for that is that it's not particularly useful in terms of cameras, and I'll mention a little bit about that later. But the second thing is that we're going to shortly find something that will actually unify all of these things together. Okay, so that we see them as the one. So rather than this being an unusual case where the points don't meet, we'll actually unify those. So at the start, we always do this. We show the concept of the central projection and then mention that there is a parallel projection as well, which we seem less interested in. But we will see later that when we move to algebra, this can all be unified, and suddenly life gets a lot easier. In effect, there are no exceptions that we have to worry about at that stage. So any mapping of one figure onto another by a central or a parallel projection, or by a succession of them, is called a projective transformation. Okay, so we could have several planes all projecting onto each other. We'll call the body of geometrical propositions which are unaffected by an arbitrary projective transformations of figures the projective geometry of the plane or the line. Okay, so this is just it's another categorization where we say that the things that are unaffected by these things, such as lines remain lines, we call these projective geometry, which is the title of tonight's lecture. The rigid body motions which preserve magnitudes and angles we will refer to as metric geometry. Okay, and metric obviously refers to measuring, and therefore if we have rigid body motions where we retain angles and we retain lengths, then we can still do calculations of lengths and angles. But obviously if we've got these projective geometries where lengths and so on change, then we can't do that. Some properties of projections are immediately obvious. For example, a point projects to a point. Okay, and you can that becomes immediately obvious that if you've got a point on one of these planes, I'll just show them here again. I've got one of these planes and another plane, and I've got a point on them. If I, from some other point, come through that, I'm clearly going to land at one other point. It's not going to converge out to a whole circle or anything like that. I'm going to converge to one point, as you can see there. So points become points. And a straight line projects to a straight line, which is maybe not as obvious, but it's what we talked about as the one thing that projective geometry does preserve is straight lines. So hence this idea of preserving straight lines. And it has a question here, so I'm going to take a drink while he's typing. Oh. Now this is an interesting question, and is asking, can central projection be done in reverse? I'm not entirely certain what you mean by that, Enda, so can it be down in reverse. Can you work your way back? So if we take this one, I'm assuming what you mean is that can that line go back to that central point? Is that what you're saying? Yeah, as long as you know the center of the projection, yes, you can. So the thing is here that if you've got a point here and you've got your center projection, you can draw a line straight through that, and it's going to pierce it at that point. So yes, is the answer to that. I think that's what you're asking me. Yeah, it's more than possible. In fact, it's actually just an extension of that. There was no reason for us to actually believe that that pi here is in between it and pi prime. It could actually be behind it. So there's no reason to necessarily assume that. In fact, we didn't actually specify that. So that is absolutely the case. So it's not. I wouldn't even. That's why I was a little bit confused about the idea of it being in reverse, because it doesn't. You wouldn't necessarily even think about that as reverse. It's just where it's placed. Yeah. Okay. It was a good question. Once I understood it. Now Vin is asking: is the plane not infinitely thin? It is, yes. Does that? But obviously, my sheets of paper are not infinitely thin here. But I'm not. Does that concern you? Have you a question beyond that, or is that just you just wanting to be sure of that? In mathematical terms, they're certainly infinitely thin. Yeah. They're 2D planes within a. We can think of them as 2D planes within a 3D world. Oh, okay. No, so they're infinitely thin, but so let's say, for example, that I'm calling this one pi and this one pi prime. They're infinitely thin, but I can move their positions. That's not a problem. Maurice is asking, is a manifold a plane? The other way around, a plane is a manifold, but a manifold doesn't have to be a plane, because these are a plane would be assuming that it's a linear thing. So a plane is a type of manifold, but a manifold can stretch to much more than that. Yeah. Okay, so great questions there. So we're on to this. So if a point A and a line L, now apologies for the you're going to see this a lot, the particular font that's used here. It's often hard to tell between an I and an L. It's something I'd like to update for next year, but I haven't time at the minute to try and figure it. So point A and a line L are incident. Okay, so they're incident, in other words, that the point is on the line or the line goes through a point. Then the following projective transformation, following a projective transformation, the projected point A prime and the projected line L prime will also be incident. Okay, so incident is just a mathematical notation for or a naming convention for this. So if a point is on a line, or if a line passes through that point, and those two things are joules of each other, and we're going to see that term come up later on again, DUAL, as in the joule operation of each other. So a point and a line being incident does not put one of them as more important than the other. So it doesn't mean that the point is more important than the line or the line is more important than the point. All we're saying is they meet somewhere. Now, if that's the case, then the projected point, wherever it projects to, and the projected line will also be incident. In other words, that point will also be on that new projected line. It might move its position on where it is on the line, but it'll still be on the line, and that's important. Okay. Now that might seem obvious from the drawing that you saw earlier. Okay. So how did they differ? So, for example, if we go back here, you can see here that this gap that gap might change there. Okay, because we no longer deal with the projective transform doesn't guarantee us that lengths and so on would stay the same. Okay. Okay, so incidence of a point in a line is preserved on a projective projection. Now, think about what we said. We started off with the idea that projective transforms, they retained the straightness, straight lines. They maintained them. Didn't maintain the length of them or otherwise, but they maintained them. And that also means that they maintain points, and it means that they preserve the fact that a point and a line are incident with each other, and that becomes useful. So as we can already see, the preservation of straight lines is leading us to other interesting properties that are preserved. We can go further. If three or more points are collinear, i.e. incident with some straight line, then their images will also be collinear. And that's what we saw back here. So collinear means that 3 points all lie on the same line. Okay? And if they all lie on the same line on one plane and are projected from somewhere which is not on either plane, then they will project all to a line that they all lie on the line on the new plane as well. Okay? Now you'll notice that I say 3 there rather than 2. Sorry, where am I? Yeah, there we are. Back here. Come on, go back. So if 3 or more points are collinear, i.e. incident with some straight line, then their images will also be collinear. Be careful to realize that the line itself does not have to be visible for this to be true. So previously I drew a nice little line for you there, and you could see that line added to the other line. Of course, in my drawing I just made those lines fit, okay, because I'm drawing on a two-dimensional plane, so I can't actually prove the thing at all. I've just shown it to you pictorially that that's what happens. But the point is that we could have three points, such as 3 points on a building, or maybe 3 points on a road that are in a straight line. And therefore, if we project that to somewhere else, or if we take a projection of that, then what we're saying is that those 3 points will appear in the image in that way, along that thing. And it doesn't matter that there may not be a nice white line drawn in between those 3 points. That's not important. What is important is that they stay collinear. So the image, there doesn't have to be an actual straight line drawn between them. There just needs to be a straight line that could be drawn between them for it to work. So what about this? If 3 or more lines in a plane are concurrent, keep typing there, Niall. Don't be afraid. I'm just going to continue with it here. So if 3 or more straight lines in a plane are concurrent, which is incident with some point, then the projections will also be concurrent straight lines. So what that's basically saying is that if I've got, and I'm going to do my best to draw this, so I've got a straight line, another straight line, and then I've got a third straight line, and they're all concurrent, which means that they all meet in one point there, then when I do a projection of that to somewhere else, those 3 lines will all meet in a point, and they'll meet in the projection of that point. Okay. Now you notice that we're doing this with 3 rather than 2. So what about the case with 2? Well, the thing is that 2 lines, unless they're parallel, are always going to meet somewhere. Okay. And strictly speaking, 2 lines that are parallel meet at infinity, and we'll be coming back to that whole thorny issue later on. But 2 lines will always meet somewhere. If you take a line between 2 points, well, if you project those 2 points to somewhere, then there's clearly going to be a line that goes between those 2 points as well. So stating the case for 2 points or 2 lines, that really doesn't tell us a whole lot. And that's why we give it for 3, because we're saying 3 and beyond. Now you're really talking. Now this is important. Whereas 2, that's almost obvious. It's almost not really telling you things. So that's why when you see the definitions of these things, you'll see them mentioned for 3 rather than for 2, and it's because 2 is kind of trivial. It's obvious that that's going to happen. It may not be obvious straight away to you, but when you put a lot of thought into it, it becomes obvious, and because it's obvious, it really doesn't tell us anything. Whereas the 3 case and beyond does tell us something. So while incidence, collinearity and concurrence are projective properties that are preserved, the measures of the length and angle and the ratios of the magnitudes are generally altered by projections. Triangles will map to triangles, but an equilateral or an isosceles triangle is unlikely to project to an equilateral or isosceles triangle after the projection. Okay, so that's important to remember about what the sort of things that could happen here. Now, something that I kind of avoided mentioning earlier, although I did just mention it on the last slide, was this idea of parallel lines and what happens with those, and of course with the parallel projection as well, which is another one of these issues. So we mentioned earlier about the central and parallel projection, and that we had to distinguish between them. Well, there is also the thorny issue of parallel lines. All lines intersect eventually apart from parallel lines. This hampered geometry for a long time because it's an exception case, and mathematicians really hate these exception cases because it doesn't unify everything together. Okay, and we parallel lines were a problem. So now you may have heard the statement that parallel lines meet at infinity. Okay, how many people have heard this statement, that parallel lines meet at infinity? I'm sure you've probably come across it in some way or other. Yeah, so I think most people have probably heard it. Okay, so the trouble with it is that that's all fine, well, but you never get to infinity, and you never see infinity, and therefore it's you kind of go, that sounds like just a fudge there. Okay, so it's a little unsatisfying and not very useful, and it's particularly unsatisfying because, of course, computers, for example, can't handle infinity, so it's not much good to us. Okay, so we need a little bit more. Now this brings us on to the idea of ideal points. These next few slides that talk about ideal points, they are what happens when mathematicians at some point have to introduce something new into the mathematics, and they have to come up with a set of rules. And so to some extent you might find that the next 3 or 4 slides really wraps your head around in a circle, and it's very confusing, but in actual fact all they're doing is they're just pinning down exactly the situation so that there can be no ambiguity about what we're talking about here. And remember, everything in maths is built on that sort of thing, and this sort of really rigorous rule keeping, and once if we're adding something, we need to keep those rules, and we need to make sure that all those rules are consistent. So that's what you're going to see in the next 3 or 4 slides. So don't be surprised if you find it a little bit mesmerizing, all the different things that we're saying, but in actual fact none of it is particularly difficult. It's just that it's a little bit confusing when you hear it first. So to make this all easier, what mathematicians sought extensions to the basic concepts that would include these exceptions in a unifying group. So that we start with the idea of points at infinity, which we'll often call ideal points. And with this, we include the idea that parallel lines meet at infinity, i.e. the parallel lines meet in one of these ideal points. Now immediately you become aware that these ideal points, or these points at infinity, they're going to be very difficult to visualize or very difficult to plot. So we can also say that a parallel projection is just a central projection, but the central point, which should be an O rather than a 0, that should be an O there, that central point just happens to be at infinity. Okay, so if we go back to that diagram and that parallel projection, we say, well, actually that's just a central projection. It just happens to be that the central point is at infinity. Okay, and that gets us around that problem. And now we've unified the two. They're both central projections, or they're all central projections, except that one of them happens to have its center of projection at one of these ideal points, and this ideal point is one of these points at infinity. So we treat ideal points just as if they were ordinary points in the plane or in space. So when it comes to the maths, we can treat them quite similarly, but when it comes to actually perceiving where they are, they're a little bit more like imaginary numbers. They're that. So we want the same set of rules that determine the behavior of points, lines and planes to persist even when these elements are ideal. So if we start doing something with lines or planes or points, and it happens to contain one of these ideal lines or ideal points, or an ideal plane or plane at infinity, then we want all these things to persist. So we declare, which is another mathematician's word for we agree. Okay, so we're going to agree to add to the ordinary points on each line a single ideal point. Okay, now if you think about it, if we've got a straight line here, okay, how many points are on a straight line? Well, there's actually an infinite number of points on it anyway. So we have all the different points here that we can have. And if we go down to really fine detail, we could just get more and more points on that. But what we've got to do is we've got to add an ideal point to this. Now, important to understand, you can't just go and add an ideal point here on the end. It doesn't work that way. Okay, so we can't show this pictorially. All we say is that on this line, there is an ideal point. There's one ideal point, and every line has an ideal point. Okay? So, the consequences of this, this point shall be considered to belong to all the lines parallel to our line, but it will belong to no other lines. Which means that if I've got another line here, which will show as blue, and it's parallel to that one, then they have the same ideal point, which I've decided again for some reason to draw it onto the end of it, despite the fact that I'm not supposed to do that. All we're saying is that those 2 points, they've got an ideal point that's been added to them, and it happens to be the exact same ideal point. Okay, so parallel points have the exact same ideal point added to them, and all lines parallel to that will have the same ideal point, because that's the point at which they meet at infinity. So the consequences of this is that every pair of lines in the plane will now intersect in a single point. Okay, so if I take another line here, we'll just we'll draw it in red this time. Okay, well, and I'll draw it straight if I can. Now you can see that that line has intersected both of those lines, and it's intersected this one here at this point and this one here at this point. Okay, but the black and the blue line, where do they intersect? They intersect in this ideal point, and that ideal point is common to both of them, and each one of them only has one ideal point. So it can't have ideal points in common with anything that isn't parallel to it. Okay. Now remember, we're only drawing on a plane here at the minute. This is drawing on a sheet of paper. It's not in the 3D world just yet. So if the lines are not parallel, then they will intersect in an ordinary point, and they're always going to intersect somewhere. So even if they're only slightly off parallel, they're still going to intersect somewhere. It might be well off your page, fine, but they're definitely going to intersect somewhere, and long before infinity. If the lines are not parallel, then they will intersect in an ordinary point. If the lines are parallel, they will intersect in an ideal point common to the two lines. The ideal point on a line is also called the point at infinity on a line. Okay? And all lines, by the way, even though I drew two lines there, what you have to remember is that as far as the maths is concerned, these lines, they continue on forever in all directions. Okay, so they always get to infinity somewhere along the way. So it's reasonable to assume that maybe that's where the ideal point is going to be put. But that's fine. You don't need to worry too much about it. So don't be tempted to think that there are two, because I actually drew that. I drew a line going in the other direction as well, as if there's an infinity in one direction, infinity in the other direction. So don't be tempted to think that there are two ideal points on a line, one at plus infinity and one at minus infinity. That's not the case. The point at infinity is to unify the idea that two lines only meet at a single point. Okay? Yeah, that is certainly the case, Enda, that we're not talking about lines with length. And bear in mind, remember, when we're talking about projections, we don't even retain length anyway. So you can see how that's not our primary concern right now. Yeah. Okay. You can certainly later on try and do measurements along lengths, but that's a very different point from what we're trying to do here. So two ideal points would mean, if we had two ideal points, which we don't, two ideal points would mean that we meet at two different points, which we can't do. So like we're meeting at positive infinity and negative infinity, which is not the case. Also, we state that through any 2 points, one and only one line can be drawn. And obviously if we've got two ideal points in a line, then that's our line, so that's a problem. Two ideal points would allow a second line to be drawn for every point. Since these ideal points would be in common with other parallel lines, effectively we allow an infinite number of lines to be drawn through the two ideal points. So basically what I'm saying is, forget I mentioned that. It's really just if it pops into your head, wait a minute, do we have one at negative infinity as well? No, we don't. Okay. Okay. But because it's something that popped into my head the first time I seen this as well, I was like, I better just make a statement about it. Okay. So do be clear on it. Okay. Now, this brings us on to the idea of an ideal line. So despite all the ideal points being at infinity, this does not mean that the ideal points are all that all ideal points are the one point. That's not the case. So if I have these two parallel lines here, right, they're going to meet at an ideal point somewhere. If I've got two different parallel lines there, which I should have drawn parallel, sorry. Okay, they're going to meet at a different ideal point, which again is common to the two of them, but it's not the same ideal point as the one for the red lines. Okay, so despite the ideal points being at infinity, this does not mean that all the ideal points are the one point. This would break the rules. So instead we agree to add to the ordinary lines in the plane a single ideal line. Okay, so this is different from our other lines. This is an ideal line now. Which again is not one that's going to be easy to draw. And this is the line at infinity in the plane. And it contains all the ideal points in the plane, but it does not contain any other points, i.e. no ordinary points. So previously we discussed a line could only have one ideal point in it, but that's ordinary lines. This is an ideal line and it can have all of the ideal ones in it. This is in accordance with our other rules that only a single line can pass through any 2 points. So Vin is asking here, sorry if it feels more like that no one can draw perfect parallel lines, hence they are destined to meet. Yeah, okay, so we can't draw perfect parallel lines. That's probably true, but mathematically they can exist. So remember that the lines I've drawn there, I can't draw perfect lines anyway because I can't draw them at zero thickness and all of that. Again, this is the maths, and this goes back to how mathematical models do not always match what will happen in the real world. So in the real world, if we've something like we've got lines on the roadway which are disappearing off into the distance, again, those won't be perfectly parallel, and of course they will probably meet somewhere, but that doesn't tell you something about the road ahead. So we do assume that this is the case, that there are parallel lines and so on, and that would be the case. Okay, and we could always accidentally get it that they would be perfectly parallel. So therefore, only an ideal line could pass through two ideal points. So if we have a line that's passing through two ideal points, it means it has to be this ideal line. Also, it cannot be an ordinary line, as it must be an ideal line, because ordinary lines must contain only one ideal point. It cannot contain ordinary points, as any line that contains an ordinary point and an ideal point must be an ordinary line. So you see how the mathematicians, they didn't sum this up in 4 slides themselves. They probably had rows for years over this, over deciding exactly what the rules were going to be. And the ideal line must contain absolutely all the ideal points, as we want to have a point in common with every ideal, or with every ordinary line. Okay, so you can see there's a lot of rules to deal with. So that's it on the ideal points, and as I say, it can be a little bit mind warping, but you know, there's nothing crazy in it. It's just this mathematical formalism. We have to come up with the exact rules. Now, there's a word of caution here, and it's when people start, you know, they go away from class and then they start thinking about this, and they start thinking about where things are, right? There's a danger where you mix up the horizon line in a 3-dimensional world with the line at infinity, which is not the same thing. Okay, so when you read texts on geometry that refer to the line at infinity, it can be easy to become convinced that there is something special about the horizon line. Now, we don't live on a flat Earth. At least I hope none of you believe that. There are some people on the internet that do. We don't live on a flat Earth, but to a rough approximation, you can think of it as just that, as being a flat plane. And as such, when you view the horizon, you might see a slight curve in it, but it kind of looks like it's a straight line. And this, the horizon is the line at infinity. But if you were beside a very, very long wall, okay, that went all the way to the horizon, I believe there's somebody in the US is trying to build one at the moment, then that would end in a vertical line at infinity. Okay, so we have a tendency to think that there's always something important about this horizontal line, but in actual fact, it's simply because we're living on a more or less horizontal plane, or at least to a first approximation. But do remember that if you were standing beside a very straight, like a building that went on for a long way, then they would meet in a vertical line, okay, or they'd meet the plane. And it's actually that they're meeting a full plane at infinity there, they're not meeting a line. So we're discussing planes only here so far, and if we think about this, we're thinking about the 3D world, so they're different from each other. So therefore, don't let the 3D world confuse you. When we get to 3D, we talk about a plane at infinity, where all of these different lines, like the horizontal line and the different vertical lines, would all meet this plane, okay? So there's a danger as well. So in the real world, all planes are curved. Yeah, I mean, on the real world, as we're living on a globe, the planes are curved, so therefore they're not mathematical planes, okay? Because of the curvature of the Earth, that's certainly true. I'm just saying that to a first approximation, we have a tendency to look off into the distance and think of this as a flat plane. So we will often do that. We'll think about the Earth that we're on from a camera view as looking at a plane, because it gets very complex if we go into non-Euclidean geometry to try and determine what the surface of the Earth is going to do. And because it's such a gentle curve compared to the position that we're at, there's very little benefit to including that in our approximations. Yeah. Okay, so how do we represent a point at infinity? So you cannot use the infinity symbol to represent a point at infinity, and the reason for that is if we talk about 10 different points at infinity for different parallel lines and we just call them all infinity, that's clearly not going to be particularly useful to us. We won't be able to tell them apart. And one of the things that we want with all of this is that when we do these things, we've tried to unify everything. We don't want a situation where we can't tell any of these things apart, because that would be no good to us. So you cannot use the infinity symbol to represent a point at infinity, as there are many points at infinity, so instead it is represented by a family of parallel lines. The intersection at infinity is just a convenient way of stating that lines are parallel. Okay, so it's for that reason rather than the other way around. And this was the exception we were trying to deal with. So these can now be dealt with just like ordinary cases. Now if we take the 3D case, in 3D we have a similar situation, but it is not as easy to get an intuitive sense of it, okay, because we can think of the plane and that's a little bit easier, but now when we go to a 3D case, it's not as easy. This is because it is difficult for us to draw the 3D version on a 2D page, so and it's difficult then for us to envision it. Nonetheless, we take the same strategy as before. We agree to introduce, again this is a mathematical term, we agree to introduce a point at infinity associated with every family of parallel lines. Each plane has a line at infinity. Okay, so all the lines on a plane, if we've parallel lines on a plane, they'll all meet. All parallel lines will meet at an individual point, and all planes will have a line at infinity. So if you can think of the world, as I say, as a first approximation as being a plane, then you think of that where it meets infinity, it meets at a line. The 2D case was introduced. In the 2D case, we introduced the line at infinity, so we have to introduce the plane at infinity. Now, there's a temptation here to assume that in the 3D case, we actually meet at an individual point at infinity rather than a plane. And the reason for this is that if you look down a tunnel, or if you stand on a street in Manhattan or somewhere like that, where you've got very tall buildings. So you've got your road, your roadway, and then you've got your tall buildings. And if you look at it, it appears to all disappear down to one point. But that's because there's actually parallelisms between the road and the walls as well. Because if you take any two of those lines, they are parallel to each other. They just happen to be parallel across this axis here. So a better way to think about that is to think about two streets that are diverging off. Okay, so they're all on the one plane here, on the horizontal plane. They've got their walls, okay, but this one appears to go that way, and this one appears to go off in this direction, and therefore they clearly meet at different places. So what happens here is that we actually have a full plane off at infinity, which you can kind of see if you just look off into the distance wherever that ends. And that's a full plane, and then in the 3D case we intersect with that. So individual parallel lines will meet at a point. A full plane will meet that infinite plane in a line, and therefore that's why we call it the plane at infinity. So we say that each ordinary plane intersects the plane at infinity in its line at infinity, which, as I said, would be a different one maybe from a vertical line versus a horizontal line versus a vertical line. Now, I mentioned this term earlier, duality or dual, where I said that if a point is incident with a line, what that means is that that point is on that line, or that line passes through that point, and that therefore they're just two different ways of looking at the same thing. In projective geometry, all theorems occur in pairs. So this is referred to as duality. So for example, in 2D plane geometry, the point and the line are called dual elements. Drawing a line through a point or making a point on a line are called dual operations. You can consider two figures to be dual if you can obtain one from the other by replacing each element and operation by its dual element or operation. This is distinct from distinct to projective geometry. Metric geometry, where we have the rigid body motions and all that, does not have this characteristic. Okay, so this is something that's quite interesting, and it's unique to projective geometry, where we have these, each theorem is a dual of another one. Okay, so you'll nearly always see two that'll go. Now, I rarely take direct quotes, and I can see in this one I've forgotten to put the little dashes down there. So I rarely use direct quotes, and I would recommend that you don't do so either. It's just that in this particular case, a lot of this lecture was taken from this maths book called What is Mathematics? It's by Courant and Robbins. It's actually a book from, I think, the 1930s, but it's surprisingly easy to read, and it seems quite modern in how it's worded. And I found it excellent, particularly in this area of projective geometry. And there was this particular passage that I thought was quite interesting to say. So the general tendency in modern mathematics is to base everything on the number concept. And in geometry, this tendency, which started with Fermat and Descartes, has decisive triumphs. Analytic geometry has developed from the status of a mere tool in geometrical reasoning to a subject where the intuitive geometrical interpretation of the operations and results is no longer the ultimate and exclusive goal, but has rather the function of a guiding principle that aids in suggesting and understanding the analytical results. And basically what this is saying is that we used to draw things, we used to draw all our geometry, and then we found that if we introduced numbers and a coordinate system to that we could actually just use algebra. And then we discovered that actually now the algebra is the main important point, and the geometry, the actual drawing of the pictures, is not that important at all. And that now it seems to be more of a guiding principle. It's there to help us to understand the algebra that we're doing, rather than being important in its own case. Okay, so this is the idea, and that's from the 1930s. So you can see that this idea had long taken hold at that stage, and the fact that we then use it later on is just part of how long it takes a lot of our mathematics or how long after you've done the maths that it can be useful. Okay, that's a worthwhile book. I don't have it here, but it's normally on the back of these books you'll have somebody will give a quick review where they'll say this is an excellent book and I'd recommend it and whatever, and on the back of this one it says something along the lines of, this is a really lucid explanation of mathematics, and it's easily understandable. Okay, and you take that statement seriously, except that it was Albert Einstein that wrote it, and you can assume that Albert Einstein's understanding of mathematics might be a little bit different from ours. So the fact that he finds it easy to understand would not necessarily assume that we would. But I did find it an excellent book, so it is worth looking up if you're ever getting into this in great detail. So The analytical or the analytic representation of a line. So to embark on the journey of analytic geometry, we must introduce numbers. We do this by introducing a coordinate frame. The two most common coordinate frames are the XY Cartesian or rectangular coordinates and the polar coordinates, which we normally give as rho and theta. So that one there is rho rather than a P. Okay, so it's the letter rho and theta, which normally represents how far out in a direction we're going and what angle we've rotated by. Okay, or at least that's what it would represent in the Cartesian coordinates, but we can just show it as two other coordinates. We saw that, I think, in the Hough transform. We looked at that previously. So we must be able to define an object completely with these. So a point is defined by one set of coordinates. A line can be defined as all the points or coordinates that satisfy the linear equation. So the full set of points that satisfy the linear equation. Okay. We've only got 8 slides to go, guys. Are you okay to go on without a break? You happy enough? Yeah, that's great. We'll get you out a bit earlier. Okay, so a line can be defined as all the points or coordinates that satisfy a linear equation. So ax plus by plus c equals 0. Now, you're probably used to the ax plus b equals y or something, or y equals ax plus b form of a line. The difference here is purely to do with the fact that we might have an x and a y input, so we're plotting this on a plane. So you can give the coordinates of a line as a, b, and c values, i.e., you need the 3 of them. Now you can see there that if we can describe them as just a vector like a, b, and c, three pieces of information, then that's very much the same as like 3D coordinates will be given that way. Okay, now this is in a plane here, but you can see how we're just giving different vectors and so on, different pieces of information. We can play about with those, and we can from that we can do quite a lot without ever drawing it. We have the analytical representation of a circle and actually an ellipse here. So x squared plus y squared equals r squared is the equation of a circle with a center at the origin x 0, 0. And if we've x minus a to be squared, y minus a to be squared equals r squared, that's the equation of a circle with a center at a and b. Then there's one for an ellipse. Now I don't give them all, but you can see here are some of the different ones. And what these basically are is an analytic representation of what would be a drawing previously. Okay, so a way we can describe that. And if we have our pieces of information, we know our pieces of information such as our a and our b here, and whatever our value here is. Whatever value we want to put there. If we know that piece of information, then we can actually work out or draw any of these figures. The whole point being that we don't necessarily need to draw them. We can just manipulate them and get an answer. So this brings us on to the final section of tonight's lecture, which is the homogeneous coordinates, which I've teased you with quite a bit. We've used them quite a bit, but I said I was going to come back to explain them. I'm going to do my best to try and explain them to you here in the next few slides. So we've mentioned these in a previous lecture and said we would come back to them. Homogeneous coordinates solve a number of problems, two principally. Firstly, they encode our new ideas, our agreements about incorporating ideal points or points at infinity. Okay, so the homogeneous coordinates encode that so that we can now treat everything the same. That's the reason that I left them to now to explain them. Secondly, they can make an affine problem into a linear problem, which is where we used them previously, and this greatly eases the use of our of linear algebra. So where we had the situations where we had things like ax plus b, which was not linear, we were able to work that by putting it into as an ax, as an a and a b. And then you had your x and your 1 there, and so on. Okay, and you could do it in that particular fashion. Okay, using them as homogeneous coordinates. So 2D homogeneous coordinates are the easiest to intuitively understand, but the 3D version is a direct extension. So if you can picture the 2D case, you can accept the 3D case. It's just harder to visualize. So take the points on a 2D xy plane. Now we're going to add a third dimension z, but this does not act like an ordinary z-axis. Move the entire xy plane out to a position 1 on the z-axis, and now imagine that the origin, which is x equal to 0, y equal to 0, and z equal to 0, is the center of a projection. Now what you're going to do is you're going to turn every point in the xy plane into a line that passes through the origin and passes through the xy point. So I'm going to try and show that to you here. Okay, where's my camera here? Okay, so let's imagine that I've decided here that I'm at point 0 here. Okay, and I've got my plane here. And what I'm going to do is I've got a z-axis that's going in this direction, pointing through here. And what I'm going to do is I'm going to move out on that z-axis here to position 1. Okay? And what I'm then going to have is the point of my pencil there, that's going to be the center of my projection. And every point that I could draw on this piece of paper here, okay, every point I could draw on that, what I'm going to do is I'm going to draw a line through that point right to the tip of this pencil. Okay? So that's the idea of it, which means, by the way, that if I take this again, I kind of need 3 hands for this, okay? That points out here in the middle of nowhere, okay? That aren't along that triangle. They can't exist in this homogeneous coordinates, okay? So this has a kind of a triangle or a cone that comes out from this, and anything outside of that around here that can't exist, okay? So I'm going to do a kind of a little drawing here for you. No, you're not limiting the xy at all. No, that can be a full plane. So what I'm going to do is I'm just going to draw you the an elevation of this, right? So because I'm on a page here, it's not as easy for me to do. Okay, so let's imagine that I'm just looking along this, and I've got my y-axis here, and I can't see my x. It's coming out of the page, out towards me. Okay. So this is my y-axis here. Sorry. And as Liam has asked, am I limited? No, this can continue on forever in all directions, and x can continue on forever in all directions. And let's say I have a point on this somewhere, and that has a point in x as well, so that could be somewhere off the page here. Okay. Now, what I do is I move this plane to position 1 on the z-axis. So I'm going to draw a z-axis here. And this is going to be position x equal to 0, y equal to 0, and z equal to 0 here at this point. Okay, we can't see the x's as I mentioned. I'm actually going to, what I'm going to do just to make my life a little easier is I'm going to pick a different point. I'm going to pick that point there. You'll see why in a minute. No, I want to delete it. Okay. Okay, now this is moved out to position 1. Position 1. Okay. Now let's imagine that my point here is, let's say 0.5. So 0.5 on the y-axis, and we'll worry about where it is on the x-axis in a moment. Okay. So that's at position 1. Now remember, I can draw straight lines projected out from this. I'll actually draw these with a different color just so that we make it clearer. So I can draw straight lines out in all directions here. Okay, but what can't exist is we can't have anything existing out in this direction here. Okay, this can't exist. Can things exist here? We'll kind of come back to that in a minute. Mostly not, but there is kind of a crossover point because technically, because back to Liam's question, I could be just going a long way down here. So there's kind of a point here at which it would almost become it would actually meet with my axis down here the way. Okay. Right, now the next thing for you here is, let's imagine that I move my plane, my y plane, out a position of 2. So what I'm going to do, just to make sure that I get the right length here, is I'm going to copy that. I'm going to move it out to position 2. Okay, so that's there. And I'm going to draw another line here. Sorry, I'll draw it in blue. Okay. Now, my question for you is, what value will this be on the y-axis? So if we're at position, we've gone out 2 on the z. What number will that be, or what position will that be? This one was 0.5. Is anyone going first? Yeah, wasn't too hard. It's a position. It's a value 1. Okay. So, or the other way I could write it is I could say that it is twice 0.5. Yeah. And if I moved it to position 3, okay, so just call that position 3 there, draw a line straight down as best I can. What position are we at there? Yep, so 3 times 0.5. Okay. So this is the speciality about homogeneous coordinates. What we're doing is we're maintaining our plane here, our xy plane. Now remember, this is going to happen in x as well. Okay, so the x and the y both change in the same way because our line just draws through it. This is not a normal xyz axis, xyz space, because it can only come out in these from this single point here. Okay, so every point. So if I take a sheet of paper here, and I take every point on this, every point on that is going to have a line passing through that point. Okay, so coming down here from, so here, so coming down through the page and down to my point. Okay, so every point now in my xy plane becomes a line in this 3-dimensional space, which, as I said, is a projective 3-dimensional space, but it's a 3-dimensional space nonetheless. Okay. Now these are called homogeneous coordinates because effectively this point now and that point are all going to be the same point, because as far as the line is concerned, if you're standing there on that line and looking at that point, you cannot see these other ones behind it. Okay, so as far as you're concerned, they're all the one point. Okay, so because they're all on that one line, and the line is what is important in a projective geometry. Okay, so it's the line that matters. That's the one line. If it's on that one line, it's the one point, and therefore the fact that it's 0.5 or 1 or 1.5 actually doesn't matter, because what we're going to find is that all we have to do is know what our position is on the z-axis. So if our position here is 3, I can divide by 3 and I get back to my original 0.5. Okay, so this becomes very important in what we do. So if a line passes through the origin x equals 0, y equals 0, z equals 0, and through a point x, y, z equals 1, where will that line intersect the xy plane if it's at z equal to 2? And it'll meet it at 2x plus 2x, 2y, and then 2 being the position on the z. Okay, so this is the case for any homogeneous coordinate. What we have is we've kx, ky, and k. And that can be whatever value. So in other words, this is whatever our position is on that strange z-axis. So this is what we meant by the z-dimension not being independent of the others. Okay, so it's not really independent of the others. It's very much related to them. So to get back to the standard coordinates, what you do is you divide across by k. So if you remember previously, I gave you coordinates like, let's say, 3, 4. Okay. And we gave that as a vector. And I said in homogeneous coordinates we would write that as 3, 4, 1. Okay, now to get back to it, all I do is I divide my 3 by 1, which is 3, and I divide my 4 by 1, which is 4. Okay, so that's doing exactly what we said there. But the point is that this homogeneous coordinate, I can multiply it by whatever I want. So let's say I multiply it by 3. Well, if I multiply it by 3, I get 9, I get 12, and I get 3. Okay, now imagine that we didn't have this, that's gone, and you now want to find out what was the original coordinate. Well, that's not a problem. What you do is you divide across by the last element. So I divide my 9 by 3, giving me 3, and I divide my 12 by 3, giving me 4. and I've got back to my coordinate. So you can see homogeneous coordinates can all be multiplied by any number, and because that last one gets multiplied by a number, everything gets retained. Okay? So this is useful, as I say, for two reasons. Firstly, it allows us to unify these points, these ideal points. You're going to see in a moment exactly how we're going to do that. And the second thing is that it allows us to deal with the affine case. So the affine case was not perfectly linear, even though it was a straight line. So ax plus b is a straight line. It doesn't pass through the origin, and that means that it doesn't obey all the rules of linearity. But ax plus b, if I take that as a point, or if I take that as a point on a kind of a two-dimensional plane, I can say that a point that a line passing through the origin on the z-axis by giving it a third coordinate, it is now a line passing through the origin, and I can turn it into linear, and that allows us then to use it as a linear equation. So that's what we're doing. We're giving it one extra dimension, but it's a special dimension in which everything must pass through 0, and that makes everything linear. So it's very useful for that, but the other place we're going to use it for is dealing with these ideal points. So now what about these points at infinity? In the standard xy plane, you would have to describe these as infinity, infinity, and there is no way to tell any of the ideal points apart. In homogeneous coordinates, you would do this as follows. You set the value of k to 0. If the ideal point is given as 3, 2, 0, this tells us we have a point at infinity in the direction of 3, 2. So now we know that that infinite point, our ideal point, separate from all the other points, because we still have the 3, 2 information. So what are its standard coordinates? Well, we just divide across by k, which in this case is 0. So 3 divided by 0 is infinity, and 2 divided by 0 is infinity. So there's certainly infinite points, but we have information about the direction that they're in. So in homogeneous coordinates, we can treat them as ordinary points that have a z value of 0. But in standard coordinates, we would have to deal with them as exceptional cases, and that would be a problem. So this goes back to, and I think it was Liam was asking about, does that xy plane continue forever? Yes, it does. It continues all the way to infinity. Now, if we've a point at infinity, and you think about the line that we're going to have to draw straight up the way in order to actually meet that point at infinity, okay? Because there's always going to be some point, and therefore our z value will be equal to 0. Okay, so how do homogeneous coordinates make an affine problem linear? Well, we turn every point in the affine space into a line that passes through the origin, and now the lines that pass through the origin are linear. So that's that problem solved. Okay, so that's how that happens. That was the kind of, I drew it as a one-dimensional case because I could only draw the y-axis at a time. You can visualize the two-dimensional case as being this kind of plane that moves off it and our lines going through it. What about the three-dimensional case? Because we've now got to have our point of projection as being a fourth dimension. Okay, that's much more tricky. It's much more tricky to understand, but in terms of the maths, it's exactly the same. There's no problems here. So 3D is not as easy to visualize, as you have to create a fourth dimension to project from, but the analytical process is the exact same. A point in 3D, x, y, z, becomes kx, ky, kz, k. And the easiest thing for us to do is to choose k equal to 1, because we've got x, y, z, and 1, and we deal with it in that form. If the point is an ideal point, k is set to 0, so working back the way, you just divide across by that fourth dimension, and once again you've got your ideal points. So one of the worries when you see this sort of thing is that you've turned now, like let's say for example that I draw on my plane, I draw a nice square or rectangle or something like that, and I want to do maybe some rotations and so on that. So if I use homogeneous coordinates, am I going to screw that up? Am I going to now have only straight lines being preserved and not everything else? And the answer to that is no. So you may remember that rigid body transformations preserved angles and magnitudes, but projective did not. And we're clearly doing a projection here when we go to homogeneous coordinates. So does this mean that moving to homogeneous coordinates loses us those rigid body preservations? And the answer is no. We get away with it because while the homogeneous coordinates are a projection, they're a projection from a higher dimension. Okay, so we've added an extra dimension. The projective uses everything, it works on lines, and those lines are retained. Okay, so we preserve the straight lines, and because we preserve the straight lines, the points that are related to them in the lower dimensions, it doesn't affect any of their other preservations. So the straight lines are all we require to get back to the lower dimensions, and therefore we don't lose any of that. Okay, so well done everyone for paying attention for that length, an hour and 20 minutes without a break. So thanks very much for your attention tonight, and next week we'll be looking at the kind of modeling the camera to do with these projections, so that it will be getting much more into the realities of it, as opposed to a lot of this abstract stuff. Okay, no problem guys, thanks very much.